Okay, let's get going with the part two recording here. So these were slides that I wanted to show today, but just couldn't get there in time. Just gotta have to vacate the class for the nursing class. Spoke a little bit about landform and some geological processes that give rise to interesting features and very influential features of the physical uh, terrestrial surface of the Earth. In this second part, I'm going to be talking about um, other factors and processes that can give rise to other differences over space, over distance, these being changes in climate mostly. When we talk about climate, you can think about that expressed in variables like temperature or in rainfall, precipitation, if you think includes snow. Um, But when we think about what gives rise to the kind of observed global variation in temperature, typical rainfall patterns, talk about things called climatic controls. These being solar energy and how they interact with the surface can vary by latitude, so by distance from the equator, north or south. Other important processes are interactions between solar energy and either land or water, and also how it affects air pressure and wind. When we talk about energy coming from the sun and interacting with matter here on Earth, call that solar insolation. Try to drag this a little bigger. So the solar radiation is kind of a magnitude, really based on the temperature of the sun. It's emitted out and it interacts with the atmosphere, clouds if they're present, and then some portion of that incident solar radiation. Kind of sunlight's extending out every direction from the sun, but the solar radiation that's incident or reaching the Earth, some of it, most of it, of some wavelengths will pass through the atmosphere and interact with the surface. And now, what happens when it interacts with the surface? Some sunlight is reflected back. So green light gets reflected by leaves. What would we think? Kind of a variety of different wavelengths might get reflected by concrete. Most wavelengths get reflected by snow. If you look at snow, it's very bright in the sun. Um, Kind of wet, damp soil, less so. In fact, water reflects relatively little incoming solar radiation. So some of that is reflected, some of it gets absorbed by the material and raises the temperature. You can think about uh, if you're outside in a summer day, sunny day, if you're walking on sand, it can be quite hot. If you're walking on asphalt or pavement, it can be quite hot compared to grass, typically cooler. Uh, Now, of the radiation that is reflected off of the surfaces, the kind that we see with our eye, some of that interacts with the atmosphere again. It doesn't bounce off the edge of the atmosphere, but rather it interacts with the atmosphere after it reflects off the surface. And then the energy that's emitted from surface also interacts with the atmosphere. And it stays around, so to speak. The heat that's then absorbed by the atmosphere is emitted. And gives rise to a phenomenon called the greenhouse effect. And the greenhouse effect, in general, makes life on Earth possible. It makes it habitable, kind of warmer on the surface of the Earth than it would be on, say, the surface of the moon, where the moon is getting sunlight too, and about as much as the Earth is getting. It's about the same distance away from the sun. But there's no atmosphere up on the moon, and so none of that energy coming from the sun that interacts with the surface of the moon sticks around, so to speak. So the greenhouse effect traps some of that energy as heat at the surface. Now, depending on the composition of the atmosphere, specifically CO2, but also could be methane, um, certain molecules will absorb and emit light differently than others. And these are these greenhouse gases. So the more of them there are in the atmosphere, the more of those molecules, um, the greater the heat retention potential of the atmosphere will be. So insolation is the term. At any given place, amount of incoming solar radiation depends on the intensity and duration of radiation from the sun. And so these are determined, these intensity and duration, by the angle that the sun rays interact with the Earth, but also the number of daylight hours. So those are two important determinants, and they're probably best displayed in a picture. So here we've got the sun in the center, and it kind of got yellow rays extending to the left, red to the right. They're all just describing solar energy. So on the right, we see an Earth, and on the left, there's an Earth too. First, taking up the right, when we talk about the angle, which determines the intensity of the sun's rays, you can think about it this way. Are these rays interacting head on, almost perpendicular to the surface of the Earth at a location? Or are they more oblique, kind of hitting it at a longer angle, in which the same amount of radiation is interacting with a larger area? On the left, we see the impact of Earth inclination, not solar insolation, but Earth inclination. That referring to the angle that the Earth is tilted relative to its orbit around the sun. And because of this, we have seasons. With the equator, if you look at any map, it's kind of flat, left to right, straight line. But if the map had a reference to the sun, it wouldn't be, or the orbit of the Earth around the sun, I should say. It wouldn't be. Earth, the equator of the Earth, the poles are tilted a bit. And so if it takes the Earth 1 year to travel around the sun, during part of that orbit, one of the hemispheres of the Earth, here the southern hemisphere, is going to have more area directly exposed to the sun. And so you're going to have longer days and warmer temperatures. And this is describing, well, kind of what the weather is right now in January, where we in the northern hemisphere have relatively weak sunlight. In the southern hemisphere, they're having their summer right now. So this, the kind of effect of the tilt of the Earth in determining the angle at which the sunlight is interacting with the Earth, called Earth inclination. So these kind of factors we call them determinants. They're very important, but we still check the weather, and we still understand that there's climatic variation across longitude, so to speak. So even if you're looking at the same latitude, you can have quite different weather, quite different climate. So other modifying variables that can determine temperature at a given location include the amount of water vapor in the air, the degree of cloud cover. In fact, trying to understand and predict changes in cloud cover is, I think, right now the greatest source of uncertainty in climate models. Also, the nature of the surface of the Earth, so this being things like topography, mountains, a plateau, elevation above sea level. So this, are you living on a mountain? Not do you live in the rain shadow of a mountain? And the degree and direction of air movement. Land-water interactions, very important in these kind of modifying variables. So clouds, right, white, and other light surfaces, here I'm talking about snow or ice, reflect a lot of the energy. So they don't absorb and re-emit it as heat. Re-radiation can contribute to lost energy. this energy that's being reflected. And importantly, water can store more energy than land. So land can heat up and cool more rapidly. Water heats and cools more slowly. Kind of as certain types of land surface can reflect more energy. So if they're brighter, say if they're sand compared to vegetation. So all these things can influence local energy budgets, the vegetation cover on land, and the proximity of water. Here's just a diagram, probably easier for you to blow it up on in the PowerPoint, and you can see with sun rays interacting with different surfaces close to one another, you get different speeds of temperature change on the Earth's surface material. Here's some review questions. Just you can pause the video and check that you know these. So air pressure caused by the weight of the air molecules above where a measurement is taken. These air molecules have some sort of a weight, really of a density, and that can change depending on the energy of the surface. So when you get within a given day, quickly warming up land compared to water, you can get relatively close or relatively short distance changes in air pressure. And what this causes is wind, air blowing from high pressure to low pressure areas. You can see it, in coastal areas at very fine local scales, but you can also see it kind of over the continent. You see movement of air. You see high pressure systems come in or low pressure systems come in. And what these have some implications for clouds, and thus because clouds are composed of liquid water, rainfall, if the concentration, particle size of water changes, such get rain. Wind, as I mentioned, air movement between areas with differences in air pressure. So climate is kind of the result of all this. And I talked about it earlier as being described in terms of differences in temperature and rainfall. And that's really the root of it. I mean, those are two pretty basic variables, and you can look at them in different ways. I say temperature, and that sounds somewhat simple, but what aspect of temperature is important? Any place the temperature is going to change. Are you interested in the maximum high, in the minimum low, in the change between day and night, in the seasonal change between summer and winter, say? And similarly for rainfall. You can talk about the overall amount of rain that areas get. You can also look at how is it distributed throughout the year. Is it concentrated in the summer? Is there monsoon systems that come in? So those kind of two base variables can be looked at in a lot of different ways. And one of the things I did in class at the very end was introduce the Köppen system. You see these climate zones described with a series of letters. And this table with the capital letters here has some of the kind of first order distinctions here. Tropical arid, mesothermal, microthermal, polar highland. Kind of makes more sense, I think, if you look at the map here. And it's very colorful here. You can see the legend, beginning with one of those capital letters, A, B, C, D, or here E, polar, so it doesn't have the H. Been refinements to this over time. But those letters aren't the only ones. That's the main climate, A, B, C, D, E. And there's a description of precipitation. This will be the second letter in these little series. Desert, steppe, fully humid, summer dry, winter dry, monsoonal. And then also a description of the temperature, so precipitation temperature. Hot arid, cold arid, hot summer, warm summer, cool summer, extremely continental. And then there are two other modifiers for polar, describing areas that are under year-round ice cover, this being polar frost, and areas that are would be ice-free during at least some portion of the year. So let me see, I'm going to try to blow this up, take a look at where we're at. Oh, right here. So in Alabama, we're the CFA, so warm temperate, fully humid, and a hot summer. It's a pretty accurate description of Alabama, I gotta say. But as I mentioned in class, this kind of CFA region extends all the way up to southern New England, where if you're American and you kind of go between those regions, as I do, you notice pretty clear differences. But then you got to think about what area is this classification system attempting to describe. That answers that in the whole world. So there are some areas that are a lot more different. For instance, kind of Central America here, northwestern Amazon basin. And there the distinction is between this AF in maroon here, AM bright red. And so the F is fully humid, M is monsoonal. There's more seasonality in the rainfall in certain parts of the Amazon or Central America than others. I mentioned in class, if you look to, especially to mountainous areas, there can be a lot of different variability. We see one large dark green area, large kind of purple and pink. Then in the mountain areas, we see some brown, some yellow, some green, some orange, some purple and pink. And it's because of, on the one hand, elevation change. So higher elevation is going to be colder. Also changes in the way that air moves over land that has a lot of elevation change. So when air is warmer, it can hold more water, more H2O as a gas called water vapor. When it gets colder, that water vapor is going to turn into a liquid and either form clouds and rain. So based on the latitudes for the US, the movement of the air is from west to east, the surface. And so when that air holding quite a bit of water vapor moves from the Pacific and encounters the Sierra Nevada mountains, you get quite a lot of rain. And that's why we've got, I think it's the CSB right here. CSB would be the Mediterranean, but up around kind of Vancouver, Seattle, these kind of temperate rainforests. And you've got quite a bit of very high elevation area, and then you've got some pine stands. So a lot more local scale, within region scale variability in climate. And you can see that other places too. The Andes or over here, kind of Afghanistan, Central Asia area. All right, I'll skip through these descriptions, but they give just a little bit more on the way that temperature and precipitation are sliced, or which differences with respect to those variables are important in denoting a main climate type. Also, how the use of latitudes kind of make a distinction here. Tropical, polar. Polar can be high latitude, kind of Greenland, Antarctica, but then a lot of the Tibetan Plateau is this polar tundra area. So it has many months of snow cover and ice cover, but also would be bare soil exposed at certain points in the year reliably. Climate versus weather distinction. This is important, and it's probably the main distinction is temporal, so over time. So weather, basically the way the atmosphere is behaving at a given moment and in a way that is of particular importance to its effects on human activities. So climate being a more long-term pattern that, again, it does have an effect on human activities, but it's not going to affect, um, whether you bring an umbrella out with you on a given day. It's going to affect, do you want to, start up an orange farm, and where are you going to buy land to do that? Kind of longer term human activities. So it says here, an easy way to remember the difference is climate is the kind of weather conditions that you would expect. It's what it would be typical. And weather is what you actually get. You have your expectations and you get what you get. Climate change, this being a change in statistical distribution of weather patterns, and one that is kind of like the effects of climate over time, observed over an extended period of time. So one way that is kind of manifest is in sea level rise. So sea level rise has been on kind of a somewhat constant increase, and this comes from two different things. The main source for sea level rise is melting glaciers. If ice is up in a glacier, as long as it's kind of held up there, it's kind of being stored as a separate stock, a separate component of the hydrosphere of water on Earth. It doesn't necessarily influence sea level rise. Now, if it melts, that water is moving from the glacial stock into the ocean stock. And so if you go back 20,000 years to the Ice Age, when glaciers were much larger and went all the way down to New York and Long Island, the sea level was a lot lower. So that's the primary driver of sea level rise, at least within historic time frame. Another component is actually temperature. So the warmer the water, the more volume it takes up, but that's a relatively minor factor. One factor that's incredibly impactful that we don't really see change has to do with geological factors. So if you look for fossils from the kind of era of the dinosaurs, you can find a lot in the interior of the US that is now, the Great Plains, but you can find a lot of aquatic animals because it was kind of an inland sea, a low depth sea. And what that had to do, or the reason for the extremely high sea level was in part there's probably no ice caps, but on the other hand, the composition and really the configuration or the shape, not exactly what is there, but how is it shaped of the continents versus oceanic crust can influence the way water gets displaced. So that's kind of a theory for why it was so high then. Temperature rise, this being a driver of the ice melt, on a fairly monotonic or straight single direction increase over the last 100, certainly 100, possibly 150 years. This slide just showing the shrinking of the ice sheets. And notice, it's a pretty clear pattern here, but there's kind of seasonal change within that of the melt and refreeze. I had in this slide showing global temperature rise in the context of recent geological past, so long ago. These two charts both show distance in time measured as millions of years and temperature change. So this top showing from 0 years ago, essentially now, back to about 5.5 million years ago. And on the bottom, just 0 to 0.8. So looking essentially at this part only of the top chart. And so there's a long-term cooling pattern. And right now, if you imagine kind of based on, I don't know, limits to production, changes to production systems, kind of a 2-degree centigrade increase, what we're looking at are temperatures that are more typical of 5 million years ago. Within the last 800,000 years, there have been pretty large swings in global temperature, but they, here we're talking 0 to 4 degrees, and that's degrees Celsius, but largely to the downward direction here. And now, when there weren't people back here then, but the kind of theories that explain this variation have to do with behavior of the Earth and Earth around the sun. These being referred to as Milankovitch cycles. Oh, I've added this little note. This material is not on the quiz. It's just kind of for enrichment here, just so you know what gives rise to really high magnitude, but also long-term changes in typical temperature. These are, I mentioned, changes to the behavior of the Earth and relative to the sun. The first being changes to eccentricity, or really the degree to which the Earth's orbit around the sun resembles a circle or becomes more oblong. And now this figure might be overdoing it a little bit, just so you get the idea. But on the scale of tens of thousands of years, there are going to be changes to the way that the Earth orbits around the sun. And this goes back and forth over, again, very long time frames. Other changes happen to the tilt of the Earth. I mentioned a couple dozen slides ago that the equator is not parallel with the orbit of the Earth around the sun. In fact, it's tilted. And the degree to which the Earth is tilted changes. It doesn't change a whole lot, but here it's seen, you see 22.2 degrees off of vertical, 24 degrees. And so these changes can affect the amount of sunlight incident at any one moment of time, can affect seasonality and accrued energy. And the other is precession. Now, this might be harder to visualize, but this is a gradual change or wobble in the orientation of Earth's axis relative to the sun. And I'll try to, maybe I should have showed these in class with my kind of arms up and down and doing a kind of silly orbit walk around, but I'll try to explain how that wobble manifests over time. But all these cycles alter properties that go back to the original concepts of today, of part 2 today, solar insolation and Earth inclination and so on. So here's some more review. And I'll just leave it at that.